Okay, so I will basically use a similar approach to what Maria presented, and that we have done together with Amon Ilakovac, Maria from Zagreb, and Professor Dominik Stöckinger from Dresden. But here, that's going to be trying to have the full list of finite BRST restoring counterterms at one loop order for the standard model when we use the BMHV scheme in dimensional regularization. Yeah, so the motivation is basically the same as what Maria said. So because we know that nature is chiral, at least according to what we observe, this means that we have chiral fermions and we have to describe them in our theories. And for instance, this is what is the case for the electroweak sector in the standard model and its extensions. And in the theory, this means that we have to introduce the gamma 5 matrix to right or left-handed projectors that apply on the fermions. On the other hand, we also use in perturbative QFT calculations the dimensional regularization, because when things work, as long as there is no gamma 5 present, it will conserve, I mean, it would not break the gauge symmetry and keep the calculations Lorentz covariant. And this is a scheme widely used in the literature and in calculations, etc. So, okay, we know that, I think, already. So the idea is that we separate the formal D-dimensional space into a 4-dimensional part, that is the physical one. And we add some epsilon dimensional contribution to it. And basically, the idea is that all vector tensor objects can be separated into a 4-dimensional part and evanescent part. Then, for instance, when we look at the matrix, we can define on this space the full D-dimensional metric as this property, the 4-dimensional one, the trace gives 4, and so on. But the problem is that when we start to look at the gamma 5 matrix, in pure 4 dimensions, the properties of the gamma 5 matrix apply to the other gamma matrices. So for instance, the anti-commutation equals 0. And the trace of gamma 5 with, for instance, 4 gamma matrices give the usual epsilon symbol, which is related to, for instance, chiral anomaly. But these properties, when we try to extend them into the dimension, they become inconsistent. Unless we do what was proposed by Toft-Veltman and then prove the consistency proved by Bratelloner and Mason, namely that the usual properties of the trace of gamma 5 with the other gamma matrices and so on can be maintained if the anti-commutation of gamma 5 holds only for the gamma matrices that reside in 4 dimensions, but the gamma 5 matrix becomes commuting with the epsilon dimensional gamma matrices. So this scheme actually has been proved to be consistent at all loop orders. But the point is that this is a consistency, but there is nothing that is said about whether the scheme conserves or breaks the gauge symmetry or the related BRST symmetry. And actually, for chiral theories, this breaking happens because basically it is due to this the fact that we have separated the gamma 5 property on the 4-dimensional space and the evanescent dimensional space. So you have a breaking of some sort of chiral symmetry. And so this means that we will possibly need to restore it later on. So as Maria already said, we know that this BMH scheme may be complicated because we will get evanescent singular counterterms. We will get new finite counterterms we need to introduce in order to restore the BRST symmetry. And so people have thought about other gamma-5 schemes. So there are a lot of alternative schemes. And for instance, in these reviews, they are discussed. But for most of them, it is not clear what happens at all loop order. So they are, it has been shown on examples or more theoretically speaking, shown that up to, for instance, 2 or 3 loop orders, they are consistent. But it is not clear yet what could happen at all loop orders in these schemes. We also know that there is this so-called semi-naive scheme for gamma-5 where basically it's only when you have gamma trace of gamma-5 and gamma matrices that you have to do adjustments. And then when you do specific calculations, you have to verify that the word identities, the Slavno-Taylor identities are verified. And if not, you do a restoration by hand of this symmetry by adding the suitable finite counter terms. There are other schemes that go further in this idea, and even instead of saying something about the anti-commuting property of gamma-5 matrix, instead abandon the cyclicity property of the trace. For instance, this is the so-called reading point prescription scheme from Kramer. But there is always the problem of whether these schemes are consistency with these two unitarity and causality, which are the two main points of QFT. And this may not be always clear for these schemes. But it has been proved to be that these unitarity and causality axioms are satisfied in the Breiteloner-Meson scheme. So basically, our idea now is to apply this Breiteloner-Meson scheme systematically. So here I will do that for the massless standard model, okay, at one loop. And what I'm going to present is based on our previous paper where we obtained at one loop generic results on generic Kirac gauge theory with scalars in addition. And the idea is to have a systematic treatment of this gamma-5 that is consistent because we know from Breiteloner-Meson that the approach is consistent at any loop order. But the BMSG scheme has still a freedom of finite counter terms. And this will allow us that when the BRST invariance is broken, when we do calculation, this allows us to restore the BRS symmetry using finite counter terms. So I will obtain here the BRST restoring counter terms for the standard model at one loop. And this, together with the singular evanescent counter terms at one loop, are actually needed for higher loop order calculations to be done consistently in this scheme. So I will present the reformulation of the standard model suited for our approach, and then the calculations, and I will conclude with a discussion. So, okay, we know the composition of standard model, SU3 cross SU2 cross U1. And we know that we can define it with quark, left-handed quark and lepton doublets, and right-handed quark and lepton singlets. We also add for the electroweak symmetry breaking a complex X doublet. But here I'm working in the massless case, so I will say that the Higgs doublet does not acquire VEV. Then the Lagrangian that defines the standard model can be separated into the gauge part, the fermion part, the Higgs part, and the Yukawa interaction part. And then there is also the gauge fixing and the ghost terms. So this is the generic notation that I recall here because later on in the presentation, I will use these notations. So that's the standard here, F mu F mu for each of the gauge groups, the standard kinetic terms for the fermions, including that interaction with the gauge fields through the covariant derivatives, the Higgs Lagrangian with the kinetic term for the Higgs and its potential, the Yukawa terms, and then the gauge fixing corresponding here to the Xi gauge and the corresponding ghost part. So to do the reformulation, so what I want here is that we are basing the calculation on real scalars and fermions. So we want basically to reformulate the Higgs complex doublet into a scalar multiplet, basically. So it is possible because by taking in separately the components of the Higgs doublet, we can reorganize them into a real scalar column vector, if you want. Then from its representation in the here, this gives us a corresponding scalar real representation, basically, that I denote by S, and the corresponding group generators are theta. Then for the quarks and the leptons, I can collect them into what I call right-handed multiplets, in the sense that I do this following construction. We can actually do that as well by instead considering just left-handed multiplets. But here I do the right-handed multiplet approach, where here I take the charge conjugate of the original quark doublet, and I associate as well the individual up type right quark and down type quark. Similar construction can be done for the lepton multiplet, but here, because we know that each of these components have a separate representation for in the standard model for SU2, then this tells you that basically these objects have a separate and reducible representation, or their generator being noted TQ and TL here. And then this allows me to rewrite the Higgs Lagrangian, the fermion Lagrangian, and the Yukawa Lagrangian using real scalars here. And basically for the fermion Lagrangian, we now see that everything is in terms of a right-handed fermion. And the Yukawa part acquires a form that is suitable with right-handed fermion and real scalars. So there is the question of extending standard model to d dimensions, and we know that basically we need to have a fully d-dimensional propagators for the fermions, otherwise there is a problem of non-regularized propagator. So we need a full d-dimensional kinetic term for these fermions, and for the interaction term, while in 4 dimensions, the gamma mu times projector right is equal to this notation, or to a symmetric projected term. This is not so in d dimensions. And in this approach, I use the solution that is the most simple, which is what I call symmetric Kira projection, where you have in both sides P left and P right. And because also it makes calculations the more simple, in the sense that it generates only the minimal amount of evanescent counter terms, for instance, in loop calculations. And this is actually not the unique way of extending the model to d dimension. So the BMHV scheme, if you want, there are many BMHV schemes, depending on how you want to extend the model to d dimensions, and each are consistent with themselves. But you have to then, once you have done a given extension, you have to work within this extension. Then the next step is that we want to restore the BRST symmetry. So we have to implement it within the model, the BRST symmetry being a residual symmetry after you fix the gauge. And this involves the introduction of the ghost field, basically. To do that, we also need to introduce these external sources that Maria mentioned for the U1 model, but they are very important in non-abelian theories. And to the original action, you add terms that have this source that I call K phi that multiply the BRS transformation of each of the fields you have in the theory. Once you have done that, when you have the BRS invariance of the theory, so at any loop order, this is done by looking at the invariance of the quantum effective action for this theory. When you have this invariance, this means that you have the Self-Taylor identities that are satisfied. So some operator acting on gamma, meaning that the variation of the action under this BRS transformation is zero. If it is not, then this means you have anomalies. And if you have anomalies, from the quantum action principle, it tells you that these anomalies should be local insertions. So they can be interpreted as local operators that have local Feynman rules. So the complete standard model action at 3 levels will contain this fermion Lagrangian with fully d-dimensional kinetic term, but fully chiral projected interaction term. And we have also added the BRS source terms in the action in order to implement the Self-Taylor identity approach. So if we look at whether the standard model is BRST invariant at 3 levels, then we see it is not, there is a breaking term. The same thing as appears, for instance, as in the chiral QPD. And this can be interpreted as a Feynman rule.
5 minutes left.
Okay, that should be fine. So now we proceed to the one loop calculations. So in order to obtain the singular counter terms, we basically look at the one loop diagrams, the self-energy corrections, the vertices corrections, and so on. So the 1/epsilon terms from these calculations define basically the singular counter term action. And when we look at its structure, we note that there is basically 2 parts in it. So there is a part that I would call the invariant singular counter term action. And this part has basically the same properties as those that we know from calculation done, for instance, in the naive gamma 5 schema. And the structure of this comes from, for instance, the usual multiplicative renormalization transformations that we know from the literature. And in addition to that, we have an evanescent contribution in the singular counter terms that is specific to the BMSG scheme. And basically, it comes from a contribution that originated from diagrams with fermion loops. So for the standard model, it has this structure where here you see that there is the difference of loop correction to the gauge boson kinetic term, if you want. So the mu nu f nu terms from the gauge bosons in D and 4 dimensions. The same thing appears in the scalar sector. And in addition to that, there are very specific evanescent contributions that are of longitudinal type for the gauge boson. So this one, and part similar to it for the scalars. And this typically causes, okay, so the group factors associated are coming from the fermion contributions. So we know already at 3 levels that the BRST symmetry is broken, and at 1 loop, at any loop order, it is the same. So in order to manage to restore it, we have to write the most generic way of the Taylor identity when there is breaking. And when there is breaking, we can show that it corresponds to having the three-level breaking as a Feynman rule, if you want, inserted into diagrams, plus a breaking originating from the counter terms, plus an extra part. And so at one loop order, which is the case I'm looking at, this expression, this breaking can be transformed into this. So there is a contribution coming from divergent diagrams, but these two have to cancel. And then there is what we want, a finite part here. And from that, there is the existence of finite counter terms that you can introduce in the theory, order by order, and whose aim is to absorb basically this finite part. And if we can find these finite counter terms that absorb this finite part, then we are fine. And we can remove the breaking of the theory. So the procedure is to evaluate each of these terms and then to define this finite counter term in order to absorb this part. Knowing that these two terms coming from divergent contribution have to cancel. So we first check that these two terms in red here do actually cancel, and this involves calculating extra diagrams with insertion of the breaking term. And this is what happens. Then, okay, then we look at the finite part. This basically is corresponding to looking at the finite contribution of the diagrams that were needed as well in order to calculate the divergent contributions here. And the nice way of this technique is that we can show that there is only a limited finite number of these diagrams to evaluate here at any loop order. And once we do that, we can find that, of course, there is a generic term that will correspond to a gauge anomaly, but in the standard model, and this is the well-known result, thanks to the fermion contributions, this local gauge anomaly do cancel. So by doing an explicit calculation, we find this condition that appears. And then from that, we can define the finite counter terms so that they absorb this contribution in blue. And they have a very peculiar structure because they are not Gauge invariant. Of course, they have to absorb the breaking of the BRS transformation that was also not Gauge invariant. And they are non-zero even if the local anomalies were removed. So the slight discussion I want to say here is that these counter terms, both the singular evanescent counter term and the finite counter term, are very necessary because when you do the renormalization and you go to higher loop orders, you need for the consistency to include them as insertions in your calculations. Okay, and the fact that there is an evanescent contribution to the singular counter terms means also that the techniques with multiplicative renormalization factors does not completely work. And when you want from that to extract renormalization group equations, there are many subtleties that arrive. Basically, these evanescent singular counter terms, their effect will dilute into the other non-evanescent contributions from the arches. Okay, so the summary is here. If I don't have time, you can read it. But basically, we were able to find the whole list of finite BRST restoring counter terms for the standard model at one loop. So to answer the question that was in the discussion after the talk of Maria, so here the approach is not process by process approach of manually restoring the BRST symmetry. This approach using the Taylor identity order by order allows you to find at once the complete set of finite BRST restoring counter term at the H bar order you are looking at. And from that, you know that if you do then particular calculations, when you use these counter terms, automatically the BRST symmetry will be restored. Okay, thank you.
Yeah, unmuting the microphone. Thank you for the very nice talk. I don't see any question. Actually, we are really running behind time a little bit. So if there is no urgent questions, thank you again. And I call in for the last speaker, Tamas Piro, with the nice title.
Hello, is the connection all right? So after all